So we are going to, we'll do notes on, which is on your page 4 here in a second. But I wanted to kind of talk to you about what I'm hoping that we can accomplish, or I'll tell you the 3 things that we're going to focus on this class period. So your homework will end up being this Chapter 27 homework part 2B, where you are asked to look at this computer printout and give statistical evidence of a linear relationship. So remember, we talked about that, statistical evidence only with a p-value. And so that's when we run a hypothesis test. So that's the first thing that we're going to be learning and talking about. We also, today, are going to discuss what this S of B is and make sure we know how to interpret that, and S of E. And so we'll make sure we know what those 2 things are and how to interpret them. So, over here, we'll start at page 4. And so on this page 4, we're going to actually take a look at our computer printout. Okay, so we have a computer printout. I'm going to kind of add some information to this because we're going to end up doing some practice on this page. So let's say that this is an analysis of trees, and we'll say that this is trees in the Aledo National Forest. So, we've already been out to the Aledo National Forest. When the 3rd day of school, we did a bear hunt. Yeah, remember when we did our bear hunt? We had visual bias because we couldn't see the green and brown bears. Okay, remember that? All right, we had more orange and yellow bears. That was the 3rd day of school. That's right. Okay, so we're going to talk about these trees. It doesn't tell you here, but I want to tell you in advance that to get this data here, I took a sample of 10 trees. And I measured their heights and their volumes, as you can see there. And so I'm wondering if there's evidence of a linear relationship here. In fact, I'm wondering, of course, that to make sure that as the tree gets higher, if there truly is a linear relationship, that as the tree gets taller, that it has more volume and such. So I want to first, actually, and next year I need to just mark this out. Cross this out because I don't want you to use this as a crutch when you're figuring out what the things are. Okay, so we're going to start off where the odds tell the evens. What in this is the explanatory variable and what's the response variable? Okay, so do that. Odds tell the evens. All right, so I think the odds tell the evens. What's what? So what would you say is the explanatory variable? Good, height, because height is explaining the response that you get, and that volume is the response. Okay, good. So we know this is our x variable and this is our y. Now, yesterday, I reminded you that in math and science, when you have a constant, then that is always a what in math terms. That's always a plain number without a variable. Okay, good. So since this is a plain number without the variable, then of course this is always going to be our y-intercept. It's not the y value, it's the y-intercept, which I think that's what some of you guys were saying also. Okay, and then of course you guys just told me that this height is your x variable. And since the height is the x variable, then that means that this is the line this is the slope. Okay, so evens tell the odds what the equation of the line is. Okay, do that now. All right, so you got that your predicted volume is negative 87.12 is your y-intercept plus 1.54 times the height. Now, I want to first discuss with you this y-intercept of negative 87.12 volume. So if we were to interpret the y-intercept, it happens when the x is 0. So I want to draw a picture of some stuff that's going on. Let's say I had this data. Then what I have going on is this kind of line. So this is my predicted y is negative 87.12 plus 1.54x. Okay? And so what's happening is I've got a y-intercept of negative 87, and then, of course, my slope is 1.54. So So I want to have a little discussion with you. Why am I ending up with this y-intercept of negative 87? Because what happens when the height is 0? What is this saying? When the height is 0, then what? My predicted volume is negative 87 cubic meters. Is that a thing? No. So that is not a thing. So we need to say, why is that messed up? Why does that not make sense? Because we need to understand that. So I'm going to explain to you why. Anybody know why? Anybody remember why? Okay. What's happening is this. The data I collected and measured these trees were somewhere, say, in this vicinity. Okay? Well, this means that my calculations confirmed that I have a linear model in that section of what I'm talking about. So what it did then, what the computer model would do, of course you say, okay, I have a linear model here. Well, then it just continues the linear model. But is it possible that your model could change, in reality? It could level out and you have an asymptote at 0, which would make sense. Don't you think you should have an asymptote at 0 so that it doesn't have a negative volume? Okay, so the bottom line is, just because I determined I have a linear relationship here where I collected my data doesn't mean that that same pattern is going to continue outside. Even up here, I'm not sure it's going to continue in that pattern. What is that called? Whenever I am making a prediction outside of the data. Yes, it is extrapolation. Very good. Pulling that back from October. That was so impressive. Extrapolation, and that's a bad thing in math. In science, a lot of times you are encouraged to do that, but it's bad here. So this year, I had a new song based on that. So we're going to listen to our Extrapolation Song. So here we go. So that's the reason that sometimes the y-intercept doesn't make sense. It was happening because of extrapolation. Okay, now, one of the ideas today that we are supposed to know is standard deviation of the slope. Okay, so let's take a look back at our little computer printout. First of all, I want to point out to you that we have this information about the y-intercept, and we said that the y-intercept is negative 87.12, but let me tell you something. Because it may not even make sense, because the y-intercept is probably, or could be extrapolation, then we are not interested in its standard deviation or running a test and getting a t-score for the y-intercept. Or, of course, we don't need to run a test about the validity of the y-intercept. So what you need to know on this computer printout is that we don't want to have these numbers. We are not interested whatsoever in the validity of our y-intercept, which could be extrapolation anyway. So you will never need those numbers, okay? All right, but we are interested in those other numbers that are on the line about slope. So we are interested in this standard error coefficient. So we want to know this number, put an asterisk there, and then we're going to go find down below the definition of what that SE coefficient. SE stands for standard error, like standard deviation. So let's find it down here. And voila, here it is. This standard error coefficient. So that is the standard error coefficient that we had up above. Okay, standard error coefficient from up above. And so here's what it says. It's the standard deviation of the slope. We remember, hold on a second. We remember that this data came from only one sample. Okay, we got a slope based on just my one sample. All right, so we expect, though, whenever other people take samples, so when Malia takes a sample of 10 trees, she's probably not going to get the same exact slope as me. okay? And when Brooklyn takes another sample of 10 people, she's not going to get the same slope as me either. But they should be relatively close. We need to know, how much variability is an acceptable amount of variability. And that's what this standard deviation of slope is doing for you. It's saying that we expect the slope to vary from sample to sample. Thus, if we gathered many samples, we would expect the slope of the relationship between the volume of the trees and the height to vary by about this many units or meters cubed, 0.3839. So that is how much we expect it to vary. I'm going to show you a picture back up here to this slope picture. Okay, so back up here to the slope picture. So here we go. We could say maybe Malia got herself some other data and her line looked like this. Well, see, she has a different slope. We're interested, how much did that slope vary? Is that an acceptable amount of differentiation in slope amounts? Someone else could have gotten a different one. Who did I say? I said Brooklyn. She got another one. Maybe hers ended up being something like this. And so, is that an acceptable amount? You can't see that. Is this an acceptable amount of changes? Differentiation. Okay. What do we typically say the number of standard deviations is okay to vary by? Good. So at that point, then we could kind of maybe tell what could be an acceptable range for slope for us not to freak out about it. Perhaps we say, oh, mine was 1.54. So if I added 2 of those standard deviations of the slope, I get about 2.3. So if somebody had a slope about that much, up to that much, I'm not going to worry too much. I mean, that's kind of getting up there. That's 2 standard deviations up. How about this? What if I went 2 standard deviations down? Then that takes me to, I think earlier somebody said that was 0.78. So that could be maybe a lower bound that I would expect to be within reasonableness. So something outside of that, outside of this upper and lower bound, would start giving me worry about the validity of our data. Maybe mine's off, theirs off, something's happening. We need to investigate further. Okay, so standard deviation of the slope. So a couple things there. Let's talk about how to interpret it. And I wanted to remind you that here in the beginning of your packet, standard deviation of the slope, while yesterday we discussed that in this chapter, the small little b represents the slope of a sample, then S with that subscript of a little b is the standard deviation of the slope. Okay, so that's how we'll notate that. This is in the very front page of the packet, so it's there to reference if you need it. Okay, so now you have these 2 songs. Standard deviation of the slope is one of them, and then we'll talk about standard deviation of residuals in the middle. But we did this song before where if you sample many times, I'd expect the slope you find of the relation between X and Y to vary this much on average over time. So in this case, we would say something like, let's actually put it to this particular problem. If I sample many times, many sets of trees and stuff, if I sample many times, I expect the slope that you find of the relationship between, and what are we talking about in our problem? The height and volume. Between the height and the volume of our trees in the Aledo National Forest. Okay. If I sampled many times, I'd expect the slope of the relationship between height and volume to vary about 0.38 cubic meters on average. Okay, because that standard deviation is the average variation that we have there. Okay, so let's listen to our standard deviation of the slope song, and then we'll go on to residuals. All right, so taking a look back at page 4, standard deviation of the residuals. Standard deviation of the residuals, anybody remember where that shows up? That shows up as just this plain S. On computer printouts and calculator printouts, it shows up as just that plain S. So let's look down lower on your page and find the information about that. Okay, so that number is 13.4. Okay, so first let's think, what's a residual? What did we discuss yesterday reminding us about what a residual is? Yeah. Good. How far your actual is away from what the expected was. Actual from predicted Y. Actual Y to predicted Y. Okay, so standard deviation means it's going to take all those residuals and average all of those residuals distances to see on average how far they are away from predicted. So this is the standard deviation of the residuals. The average amount that the observed values, so the actual Y's, differ from what they were predicted to be. And in this case, it said was 13.4. So if I got a tree with a particular height, and it had, say, it was 13.5 cubic meters above what I intended it to be, the volume, then I would not be too alarmed. I think that's just a little bit more dense tree. We had a little bit more, had better weather, or I don't know, whatever it was that contributed to that. So, the average amount that those actual Y's vary from the predicted Y's. And so that is what we find. Oh, on page 9 in your packet, you end up with these pictures here. So I want to talk to you about those. So on page, right after page 8, I don't think it's actually numbered, page 9 here, we've got this. So we have, here is, again, here's our residual plot. And of course, this is our prediction line here, our LSRL. Okay. So what I want you to do is think about this. Here is our, our one standard deviation away. So 13.4 in this case. So do you remember when we do normal model, the 68, 95, 99.7 rule? So we have all of these observed, and about 68% of our actual data should be within one standard deviation of that prediction line. Okay, about 68% of the observed data should be within one standard deviation. And then look here, 95% of the actuals should be within 2 of those standard deviations. So 13.4 times 2, 26.8, and so on. And then, of course, 99.7 are within 3. Here is what it might look like as three-dimensional, where you show this prediction line, your expected value. Your expected value is the mean. If you think of this as a three-dimensional normal model, kind of a mound of data coming out towards you, you've got 68%. You've got much more clustered around the line, the 68%, and then it spreads out. Okay, so let's go to our song so we know the exact way that we should translate or make a statement such as this. Okay, so let's do it in terms of our trees and volume. So the average amount that the actual Y value point, varies from what's predicted to become, varies from the predicted Y. So I'm going to start it off just like that. The average amount, so here's an example of what you might say. The average amount, the actual, and what's my Y in this problem we're doing? Good, the actual volume. The average amount that the actual volume varies from the what? The expected or predicted volume is about, in this case it said 13.4 cubic meters. So the average amount that the actual wise will vary from predicted is about that much, okay? So again, I can think in terms of 1 or 2 or 3 standard deviations away from predicted and not be too alarmed. Okay, so we'll listen to that song here in just a second. I know I'm making you go back and forth between all these pages and such. So on page 10, you can see problems 2 and 3, I was asking you to use this computer data down below and interpret the meaning of the S of B and the S of E. So S of B, what is that? What is this S of B thing? Standard deviation of the slope. Good. And I forgot to mention to you that, and again, over here in the front of your packet, when we have the summary stuff right here, that... look at here, this is or just look up here, you don't have to necessarily turn to your thing. Right here, this is interesting because the standard deviation of the residuals is you need to know, you'll see it in 2 different forms. You'll see it as just a plain S, and sometimes you'll see it as S with a little E. The plain S is typically what is shown on the computer printouts or in the calculator printout, okay? But the S with the little E is usually what the notation that a person would use to write to clearly differentiate it from the other kinds of standard deviations that we have. So that's generally the notation we use when we are writing. Now let's talk about why it's E. So the reason, I just did that. So the reason that it is, let's go back to whatever that was. Why did it do that? I don't know. So the reason that it is S with a little E, the reason that it's S with a little E is because they kind of think of those residuals as, quote unquote, errors. Errors, E-R-R-O-R-S, because it's the actual is not exactly what it was predicted to be. So it's off from the predicted, so it's an error, quote unquote error. So that's why they have that little E. Okay, so that's what you'll be doing then on that page 10. All right, the last thing for today that I want us to do is making a, I got writing that is off from, so let me see if I can't fix this here. All right, so there we go, not too bad. So the last thing I want to do is do actually a phantoms model of this problem, okay? So let's actually use this information on this page and do a full phantoms. Now, unfortunately, you don't have a place in your packet, and again, this is on page 4. You don't have a place in your packet that's a blank page to do this. I've kind of decided to revamp this lesson this year, but on the very back of your packet is a totally blank page. So if on the very back of your packet you wanted to do these notes there in the phantoms model of this, we can do it. Okay, so let's do our phantoms. Here we go. All right, so do you remember what the a linear regression test is actually a test about? Do you remember what the linear regression test is actually a test about? To see if there's a linear relationship. But in order to do that, it's actually testing slope to see if there is a slope, a constant slope. So what we want to do then is we want to define. So in our phantoms model, our parameter P, when we would do proportions, the first thing we would write is P equals what? The proportion of blah, blah, blah. When we would do means, we would write mu equals the what? Mu equals the average, blah, blah, blah. Well, with this, the letter that we use to represent the slope of the whole population is not little b, but capital beta. And so that looks kind of like a Greek capital letter beta. Kind of looks like this. Okay, so that is the slope of the whole population. So we always start this by saying the slope of the relationship. So that is how this always starts. The slope of the relationship between, in this case, height and volume of all trees in the Aledo National Forest. Okay, very good. So what would come next in our phantoms model? H. Okay, so we want to do null hypothesis and alternative hypothesis. So HO. So we're going to say, hey, HO means no linear relationship, nothing fancy happening, not a big deal. So how could our slope look if there was no linear relationship? What do you think the slope might be? Yep. So we would start off saying the slope is 0. There is no, and that implies no linear relationship. All right. With, of course, HA, and in this case, we had discussed at the beginning of the class that I hypothesized that as I get a taller tree, I'm having a higher volume. So I'm going to use that one-tailed. And this, of course, says that there is a slope. There is a slope other than 0. There is a linear relationship. Okay, so that is our hypotheses. Okay, A in the phantoms model is our what? Assumptions, and normally we get real, but we're going to get line on this. And we're not going to do those yet. They're a little bit different than get real, so those get saved for another day. We're going to do these another day. So on your homework, you do not do the assumptions yet. You get to skip them so far. So that's nice. We like that. Okay, N is going to be the name of this. Okay, so the name of this is a linear regression t-test. And so we're going to talk about why it is t. While you're writing that out, I'll talk to you about that. Linear regression t-test. So it's quantitative data. Okay, so it's not categorical. So we're not doing proportions, we're doing means. Our t's are with our means and we only have the samples standard deviation. So if I only had the 10 trees, I know the standard deviation of just those 10 trees. So because I don't have the standard deviation of the population, hence t distributions, not the perfect normal model. Okay, what is the next thing in our phantoms model? Good. T is the next thing in our phantoms model. And what is the T in our phantoms model? The test statistic and our p-value and our degrees of freedom. Well, let's look at this computer printout. Look at all of our slope information. I want the evens to tell the odds what they would guess the t-score and the p-value to be. What do you think about page 4's computer printout? Looking at all that, what do you think the t-score is? There we go. It's not supposed to be some kind of mystery. The t-score is 4.02. The p-value is 0. Okay, so looks like we got some good evidence going on there. So our t-score is 4.02. Our p-value is 0. Now, remember, I'm supposed to tell you degrees of freedom. So we're going to do a rapid-fire review of degrees of freedom. Okay, let's see. Grace, what's the degrees of freedom for just a mean, regular, plain mean test? Nope, not categories. Just sample size minus 1. So n minus 1, Okay, remember that? That was our first degrees of freedom we learned. Okay, Clayton, what is our chi-squared goodness of fit degrees of freedom? Categories -1. Okay, good. Colby, what's our degrees of freedom for chi-squared homogeneity and independence?
Rows -1.
Good. Rows -1 times columns -1. Well, this is most similar to our regular old t-tests. So it's going to be close to the n-1, but we have two variables, an x variable and a y variable. Therefore, it is n-2. So this is the last new kind of degrees of freedom that we have to remember. It is n-2 because of the two variables, which in this case, I had told you I had a sample size of 10, so my 10 minus 2 meant my degrees of freedom on this problem was 8. Okay, good job. What's next in our phantoms model? Oh, obtain a p-value and compare it to alpha. So our p-value of 0 is less than our alpha of 0.05. So we will make a decision, and that decision is to reject HO. Very good. And so we'll state our conclusion. Since the p-value is less than alpha, I'm rejecting HO. And my evidence statement is always about what? HA. Evidence is always about HA. So in this case, I want the evens to tell the odds. If you have evidence of HA or if you don't have evidence of HA, write it out in context. Go. Okay, very good. I hear it all. There is evidence, because we rejected HO, there is evidence of HA. There is evidence of a linear relationship between the height and volume of all the trees in the Aledo National Forest. Okay, so that is a statistical evidence with a p-value of a linear relationship between the height and the volume. So, and that's it. So no biggie there, all right? So then assignment-wise, what I want you to do is go on over to page 10. And again, 11 was a blank page so that you have room to write. But let's go ahead and investigate our problem here on page 10. Here we go. Our problem on page 10 says, we looked at, they had data from an October 2002 Consumer Reports where it listed the price in dollars and the power in cold cranking amps of an automobile battery. So they were wondering if more expensive batteries are generally better in terms of starting power. And so here's some software displays. They did several of them. We're not going to focus on those graphs. We'll actually use those for our conditions another day, our assumptions another day. So I want the odds to tell the evens what the standard deviation of the slope is. I want you to find the standard deviation of the slope in that computer printout. Okay, so since the cost is our x variable and that line is about slope, what did you decide? Let's see, odds told the evens, so the evens tell me who's even there. Okay, Grace, what's our standard deviation of the slope? Good, 1.282. So this is the S with a little subscript B. That's the standard deviation of the slope that you would say if we sampled many times, I'd expect the slope you find of the relationship between cost and power to vary about this much on average, blah, blah, blah. Okay, guess what? The opposite, the other way around, evens tell the odds now. The standard deviation of the residuals. What's the average amount that the actual Y will vary from the predicted Y? So find that. Interesting.
Significant
So while you're looking for that, I just wanted to point out to you, here's a residual plot picture. Notice, here's the prediction line, and most of the data is within one standard deviation of that prediction line, about 68%, and 95% is within 2 standard deviations. Okay, so what ended up being the standard deviation of the residuals? Go, Tyler, what is it?
116.
Good, this 116. Also, what's another way we would notate that instead of just plain S? S with a little E. Very good. Okay, so there is your start on all of that. I want you to do your 10 and 11, so all you have left is do the interpretations and your phantoms.